All right, so first some issues very quick. Apparently some of the people, including me, cannot see the attachment with the description of the first project. I'll remedy that after class. So in about an hour, should be done. The other issue I want to mention is which actor library to use, right? So you can use the actors in Scala, or you can use the Akka actors. My strong advice is switch now to Akka actors. The Scala actors are nowhere close to the scalability of the Akka actors, right? Two reasons to do this. One, I mean, there are differences between the two. So you learn one, you switch to the other, and you keep on making mistakes, right? The Akka actors, much more scalable. And if you really want to brag after you took the class that you did some large-scale actor model programming, much better to brag about Akka. Has enterprise support. It is the only one that's actually used in industries used out there, okay? So trust me, you want to do Akka from the beginning. There is almost no difference as far as you're concerned, and Akka has better tools to figure out what's going on in the system, timeouts, all of that stuff. It's much nicer in Akka compared to the Scala actors, okay? So just do Akka. All right, good. So the topic for today is going to be processes and anything related to processes. I'll focus first on a more classical view of what these processes are, processes and threads. Next time we're going to switch to how they can be used to do things, okay? So let's try to make this a little bit more interactive. What are these processes? All right, so, I mean, you've been using computers for a while now, right? And when something goes wrong, you go and kill the process. What does that mean? What's the process? I mean, what's the purpose of the process? That's maybe the first question to ask. Why have processes in the first place? Why not just run? Yes?
I mean, it represents a copy of a running program in memory along with all the data that the operating needs to
right, so the first shot at this is a process is some nice abstraction to organize the combination executable data and maybe something else mysterious in there. So yeah, that's true. But what else is a process? Especially in modern operating systems. How many people here ever had to run anything on Windows 3.11? So by the way, that was called Windows for Workgroups. And when Linus Torvalds released the kernel 3.11, the Linux kernel 3.11, he called that one Linux for Workgroups, kind of a tribute for Windows for Workgroups. Okay, well, joke. So, any of you ran anything on Windows 3.11? Okay, so what was one of the properties of Windows 3.11? It had processes, no problem. It was one of the first operating system in the line of DOS, so the kind of mass distributed personal computer operating systems, right? DOS could really run only one program at a time, right? So DOS didn't really have processes. DOS had only one process, technically. It had no ability to switch between processes. You had to reboot the operating system to run another program, really, right? So Windows 3.11 had processes. You could run multiple things at the same time, but it did not have another property that we find in modern processes, which is any sort of protection between processes. So essentially, you have the abstraction, kind of the separation. You can run multiple programs at the same time. They have their own data. They have their own executable. But what they don't have is any kind of way to prevent one process from trampling another process. Okay? So essentially, what you could do, one process could write anywhere in memory, including in the memory of another process. Actually, there was no memory of a process. There was only memory. And you could write anywhere you wanted, so you could play nice or you could not play nice. If a process hung for any reason, the whole system was down. Why? Because a process actually had to voluntarily give up the CPU for another process to run. So in fact, what you had there is virtually none of the good part about the process. Is just a little bit of an abstraction in the sense of, yes, you have multiple executables and some help. So processes are not only about this separation, right, that you can run an executable and there is some data for it and whatnot. but it's also about protection, protecting one space versus another space. So a process creates a space. It's in fact a complete space, right, that simulates completely a full machine to a large extent. Right? From process's point of view, the memory looks flat. Right? You have your own data, you have your own things. Nevertheless, you can have multiple processes on the same machine that cannot destroy each other. Now, a number of questions there. I mean, first of all, why is this needed? Because it's so hard to write programs that never make mistakes. Right? So if you have some sort of a very low-level mechanism to offer this kind of a protection, right, then you're not so worried about the mistakes, because if the process runs amok, you just find a way to kill it, and that's the end of it. Okay? So an important characteristic of this is the operating system, who supposedly is the guardian of these processes. That's maybe what the operating system should do, right? Should have the ability to manipulate these kind of processes, even when they don't want to be manipulated, right? So for example, in Unix systems, you can send signals to processes. That's a nice way to say, hey, this happened, or I want you to do something. But there is one signal that's non-negotiable, and actually the process is not told at all anything. It's the signal number 9. What's the signal number 9? The kill signal. So what does the kill signal do? Well, the kill signal, when you send a kill signal to a process, that essentially makes the operating system take down the process, no questions asked, and the process doesn't even get the chance to say anything. It's a last resort mechanism that allows you to take down a rogue process and not take down the whole operating system. So this is really the fundamental difference between Windows 3.11 and, let's say, Windows 95-ish, that you could kill processes and still run the operating system, right? Now, how this separation is done, well, it needs significant hardware support, okay? And that's where the virtual memory comes in, and that's where all the protection mechanisms come in. They showed up in, well, they showed up in computers early on in the 60s, but they showed up in the cheap computers, personal computers with the 386 line, right? So what's the oldest processor anybody here has ever ran on, executed, did things on, played games on, whatever? I'm trying to figure out how old are you guys. So, so how many people owned or know somebody who owned a 386 processor? Okay, 386. I have two 386 here, 5. 486, Pentiums, right? It starts to get, well, Pentium is kind of a very diluted name now because they're all kind of Pentiums, whatever, right? So even Xeons, right? Pentium, Xeon, something, they still Pentiums. Okay, you all probably own some sort of a Pentium. All right, so the 386 is the first processor that had hardware protection. Without hardware protection, it's impossible to have any kind of operating system protection. Why? Because again, it's a matter of how do you take control away from a process. So how does the CPU take away control from a process? Oh, by the way, first question is, why are we talking about this? Why suddenly in a distributed systems class, when we are supposed to talk about many machines and how they talk to each other and how they do things together, we talk suddenly about processes? Because ultimately it boils down to this. This is what the low-level implementation is. And if things run amok, that's where you have to do certain actions, right? So it all starts with those processes. Because in the end, any modern operating system at the lowest level will run processes, okay? Or maybe something more, which we are going to see in a few minutes, okay? So you need a hardware mechanism to take away control from a process. That essentially means that you can stop a process and start running something else. And there are many such mechanisms. I don't want to go into all the details. They are all related to this kind of interrupts. Okay? So an interrupt is a piece of code that executes when some external event happened. And one particular external event is a clock interrupt. So you can program an external clock to say, wake me up 1,000 times a second. By the way, that's about how often a modern operating system programs the clock to be woken up. Okay? So wake me up every millisecond. And every millisecond, you can look and say, hey, you know what? I'm going to take away the actual real CPU from this process and run something else. Right? And that happens all the time. And this is called preemption. Right? So preemptive execution, this is, in fact, non-collaborative preemption, in the sense that it doesn't matter if the process wants to be to have the processor taken away from it or not. The operating system can still take it away. how those special interrupts, they are programmed and fired up at the lowest level in the processor. Some code runs. The code can actually switch who runs. How can you switch which program runs? What exactly does it mean to switch between processes? What goes on in there? Ultimately, this is a question of what do processors do? So what do processors do? The CPU. They execute instructions. So they have memory, and they have instructions, and they execute the instructions, and that they change the state. The state is things like registers, caches, main memory, external devices, and whatnot, right? So to take away the CPU from one process really means start execution instructions of another process. So it's all in some sense virtual. It doesn't really exist. It's just another bunch of code, of instructions. Okay. Now, these kind of things are important because allows a very precise definition of what a thread is versus a process, right? So, I mean, everybody here knows about multi-threading. What's multi-threading? Right, so we are now playing with words. So what I want you to understand is saying the words that you hear doesn't mean you really grasp what's happening. So lightweight process, what makes a process lightweight? I'm sorry? So 1 second, guys. So Right. But what I want to do is zoom in on this lightweight thing. So lightweight means it has less weight. What does it mean here? What's less here?
It is running on multiple threads.
Yeah, but what does multiple threads means? Right. Well. So, OK. So let's see. No, but what I want you, so let me tell you what the purpose of this discussion is. The purpose is to develop this ability to zoom in and really understand something. Because until you do so, you're not going to be able to really tell what's going on and why it's going on. Okay? So what I want to instill in you this ability to run away from just big words and really understand precisely what makes it tick. Because once you do that, it sticks with you forever. By the way, these ideas are 40, 50 years old. They did not change. This separation between process and thread and whatnot. Okay? So you have to stay away from overly big words. So they don't share memory. Of course they share memory. The physical memory is shared by everything on the computer, right? So there is something else that they don't share. What they don't share is that protection area, right? So I just mentioned that in order to isolate processes, the operating system it's creating these virtual spaces. You cannot snap out of it unless you do very special instructions, which the operating system takes full control of. Literally, in a processor, you can basically specify is if this bit is off, you cannot run this set of instructions. So those are the instructions that can manipulate these virtual spaces. This is what the virtual memory system allows you to do. So, by the way, what's virtual in the virtual memory? What does virtual mean? We are going to talk about all kinds of virtuals in this class, right? Virtual processors, virtual hardware, what's virtual there? What's going on in there? There is some sort of an indirection going on, right? Things are not what you think they are. So the process might think that its memory starts at 0 and goes to whatever. But in fact, when you go to the real memory, it's nowhere close to 0. It's all over the place. So there is some sort of trickery going on, and there is some sort of a mapping going on. Who does the mapping? Well, operating system cannot do the mapping. Actually, it can, but the performance would be abysmal. So they did this a long time back for processors that did not have support for doing this fast, right? So it's called software virtual memory. Truly horrible. I mean, truly horrible. Because every time you need more resources, right, or every time you need to do some translation, you have to ask the operating system to fire up one of those interrupts. Performance is abysmal. It has to be done in hardware. That's where, when you want this kind of a decent support, right, you need to convince Intel or AMD to support it deep into the hardware. Okay? This mapping between real memory and virtual memory, it's done, in fact, by the processor. And it's done very deep in the processor. Right? So this is where you start hearing about all of these gizmos in modern processors, like the entire virtual memory subsystem together with special caches to accelerate the translation. So the translation is done all the time, but it's done through a cache. So that once you do the translation, you don't do it over and over and over on every memory access. So in principle, right, so we have here the real memory. So this is what you would call memory. And by the way, whatever we call memory doesn't even look like this, okay? Because it's different memory SIMs that get plugged in on the motherboard. So there is even more virtualization, even with respect to whatever low-level view the processor might actually give you. Right? There is not even one processor now. You have many cores, and they might control the memory in very weird ways. So it goes on and on and on. I mean, until you get to transistors, it's all virtual, basically. Okay? All right. But anyway, let's not go all the way. Memory, it's flat. So this is whatever my physical memory is. Now, from the point of view of a process, and actually not from the point of view of, well, with special instructions, you can access the memory at this level, but not without special instructions. Actually, even with special instructions, what you can do is just switch the mapping that I'm going to describe now. Virtual memory, it's what any executing anything sees. Now, I'm not saying process, because at the level of the hardware, processes don't necessarily exist. Processes are an abstraction introduced by operating systems. It's just most of them introduce these processes, but they are not necessarily at the level of the hardware. Okay? So let's call them execution contexts, whatever that means. Okay? So this virtual memory, it's some sort of a flat memory space. Okay? Anything executing only can talk about this flat memory space, and then there is a translation between the flat memory space in here and the real memory. This kind of a translation allows a great amount of flexibility. I mean, really great amount of flexibility. I'll mention some of them in a few minutes. Okay? But the important thing is to understand that you're only running in here, which means the translation between the virtual and the physical memory goes on all the time. Okay? So who specifies how the mapping is done? Special tables. Okay? So there are special tables, special dictionaries, essentially, right, that specify the translation between the virtual memory and the physical memory. Now, that's done, the actual translation is done by the processor. So literally, you can tell any modern processor, hey, here is a new translation table. And then in hardware, it has all of those mechanisms to look up fast in tables. Of course, if it finds weird stuff in the tables, it's going to start screaming in the form of a special interrupt, right? So it has special signals that can be intercepted to say, this table is messed up, right? So really, what the operating system does is it does one of the things. It does the manipulation of these special tables, okay? Special mappings between the virtual memory and the physical memory. Now, the operating system can do anything it wants in those tables, okay? Now, why is this important? Well, it is important because it allows you to understand how you can do certain kinds of magic, okay? And there is large levels of magic that actually can be done, okay? Now, the operating system, in fact, has the ability to give the same table to different execution contexts, okay? If you share completely a virtual memory table, you essentially get those threads. So saying that the threads are like processes, but they share the memory, what you're really saying is that the threads share the same virtual memory table, okay? That essentially means that they see the memory in the same way, right? But that doesn't mean that's not possible to get two different processes to share the memory. And by the way, there are shared memory mechanisms that are implemented precisely in this way, right? So one of the gizmos in modern operating systems is inter-process communication. They are basically free forms. I'm going to come back to them probably later as well. One of them is shared memory. So how do you do shared memory? Well, you just make sure that they map the same region in the real memory somewhere in their virtual memory. So then any change any of them does, it's instantaneously seen by the other one, okay? So this is one of the things going on in the processor. The other issue is this execution context. What exactly does that mean? So how do you, I mean, it's all about, and by the way, this is very important when you talk about virtualizing hardware. So suppose I want to capture the state of a of a process. Why would I do that? Because I could do things like move it on another machine and do other things. Okay? What's the state of a process? What would I need to remember in order to resurrect the process? I mean, if you figure out a way to kill it and then resurrect it, essentially you answer the question of what you need to remember in order to make it alive again, right? So kind of what's the soul of the process so that if I recreate the soul, it ticks again? Well, I have to capture all the state, right? Or I have to make sure that parts of the state that I cannot capture are recreated. And why am I saying this? I'll mention in a second, okay? Because certain things you just give up on them, okay? So, I mean, of course, the whole virtual table, I mean, it has to be consistently maintained between various incarnations of the process, let's say. And by the way, this is what's happening if I take away the processor from the process. If I take away the processor, then I let somebody else run, and it's going to be clear in a second what exactly does that mean. But if I want to come back to this process, I have to recover the state of this process, okay? So, same mapping for the virtual memory, but that's not a problem if it's on the same machine. But it's a tremendous problem if it's on a different machine, okay? So part of the challenge of moving code around is going to be make sure it has the same virtual table, okay? Or at least the virtual memory looks in the same way. Other things are registers. So what are registers? How many people took a hardware class again? Well, you should all take, right? Registers are these locations of special memory that can be accessed at extremely high speeds, right? You can access multiple registers in the same clock cycle, right? Most of the instructions can manipulate, I mean, virtually all the instructions manipulate only registers and combinations, registers, and memory, right? And some of them can actually span 3, 4 registers. A single instruction, then it can run 3 of those instructions in parallel, right? So registers are these memory locations. I mean, the size of the register is dictated by those bits of the hardware, right? So 32 bits usually means most registers are 32 bits. 64 bits means most registers are 64 bits, okay? Now question, on your laptop, what's the size of the largest register in bits? I mean, 256?
Well, it's kind of a virtual register for like some of those extra wide AVX kind of instructions.
So who knows what AVX is? Who knows what SSE is? SSE? No. Well, you see, that's the problem with computers. I mean, they keep on inventing these acronyms, right? You go nuts with them. SSE. By the way, before SSE, it was MMX, right? MMX. I mean, if you remember if you ever programmed in MMX, you're too old, basically. I mean, this is really long time back. Then they switched to SSE, and they went from an implicit version 1 to some funky 4.2 or 4.1a, or, I mean, they ran out of numbers and they switched to letters also. It's all kinds of variations. And now it's the new AVX. And AVX, and now they have an AVX2, right? Do you know what AVX2 is? This is the 512-bit wide instructions they have in the Phi processor, right? So what these things are is special instructions to do floating point arithmetic that are needed for games or multimedia. This is the kind of stuff that usually graphic cards do, but you want to do them on the processor and to do them fast enough. And one of the hallmarks of this is the registers get wider and wider, right? So MMX had 64-bit registers at the time when everybody was 32 bits. SSE has 128-bit registers, AVX 256. I just mentioned AVX2, the super wide AVX by using the Phi processor 512. And essentially, these are very wide registers that can even be viewed as sub-registers. Actually, almost always, you can view registers as sub-registers and do all kinds of things with them, okay? In particular, floating point operations, which are extremely important for this class of instructions, but also some integer operations, okay? Good. Why is this important? Because you see, if you use this kind of large number of registers, the state of the process, right, consists in all of these registers. If you know a process doesn't use AVX, you can avoid saving AVX registers. Now, they're already pretty large, right? So you have to save quite a lot of information when you say capture the state of a process. So the state of the process is for sure the collection of all registers, okay? Except maybe the super special registers that the operating system manages, okay? What about other things? So the memory we dealt with because it's the virtual memory system, okay? Now there is a particularly important, this is more important for performance, but I want you to get some broad overview now, right? The mapping between the virtual memory and the physical memory is done through a special kind of cache. What are caches, by the way? What do caches do? Why?
Because it could be faster. It has a hierarchy, and top is the cache, and then memory, and then disk.
Okay, so let's backtrack a little bit. Okay, so caches are all about trying to give the illusion of speed by using a small amount of much faster something. Okay, so when I talk to people that don't have a computer science background, I give them. By the way, caching is a universal technique. A lot of scalability in distributed systems has to do with caching. A lot of the weird names in distributed systems map, in fact, to some form of caching. Okay? So the situation is like this. I mean, the simplest situation. I need to do work, and I need to access all kinds of books. Right? I have the book I keep in my hand, which I have the fastest access to. I have my desk, in which I can keep about 10 books, and I just have to stretch my hands. I have bookshelves in my office, so I have to stand up from my chair and go and pick the book and bring it if I don't have it in my hands. And then there is the library. And then, well, there is this interlibrary system, so I can order a book, and in a month I get it. Okay? So in principle, I have access to these billions of books, but it might take forever to get the one. Okay? Good. So how do you make a system run very fast? Well, a simple technique would be keep the books you read very often. For example, if you read only one book, just keep it in your hands and don't even put it on the desk. Okay? If you kind of know, I mean, if you only have about 4 or 5 books you read very often, as long as you have a decent policy in which you say, hey, if I access a book, I'll take a book from the desk and move it in the bookshelf and then put the new book on the desk, then you're going to find it on the desk. Right? So suddenly what we're talking about is, if I have some idea how I'm going to use resources in the future, I can come up with a policy that allows me to use a faster kind of access. But it's all about if I have some idea what I'm going to do in the future. Right? Now, you can so traditionally, caches are essentially described and used in this way. Right? Once I pay the high price to bring a resource, I'm going to put it in my closer. Next time when I use it, it's going to be there. Also, you can think of, once I access a page in the book, it's quite likely I'm going to access other pages. So then it's right there. It's close in the cache. Okay? But there is an even better scenario, and we're going to come back to this when we talk in general distributed systems, which is if I know in advance what I'm going to do, I can make the request way ahead of when I need it, and by the time I need it, it's right there, closer in the cache in my hand or on the desk. Okay? So this has nothing to do necessarily with once I pay the price, it's cheap to access, which is what a normal cache would do. But I even know in advance what I'm going to do, and it's there when I need it. For example, in a distributed system, if you know that you're going to need a certain kind of data in the next second, you might as well request it now. You go do something else because you don't quite need the resource, and when you need it, it's right there. Or if you could anticipate what the user needs. For example, if the user starts reading a file, right, you could essentially, and it accesses only the first block in the file. You could start bringing the other blocks. So for example, if the user accesses the first block in the file, the second block in the file, the third block in the file, by then you should figure out that it's going to access all the file in order, and you start bringing the blocks way before the user says, give me the block. If you have enough room in your cache, that essentially is going to mask completely this large latency to go and bring something from the cache, so from the faraway place, right? So this kind of prefetching, it's what will provide kind of the biggest speed ups when it comes to any system, not only distributed systems, right? Okay, so we're going to come back to this. Now, essentially, these caches are everywhere. They are everywhere in hardware, and they are emulated everywhere in all the things that are built on top of the hardware. So ultimately, modern systems are all about caching. And it can make a tremendous difference in terms of the performance of the system with respect to what you cache, what do you keep in the cache, and when do you fire up the request for the cache. By the way, the processor you have even in your phone, well, your phone not so much, but the laptop definitely, it's extremely smart at this prefetching. Literally, the cache detects when you do some sort of a nice linear access, and it's going to start making the request ahead of the time you actually need them. So when you need them, they are in the cache and say, oh yeah, it's like having a fantastic secretary that kind of knows at what speed and how you're going to do things, and just brings them, and they are always on your desk. Fantastic, right? So that's caching. Now, when it comes to the virtual memory, a special cache is used to do the translation between virtual and physical memory. Because otherwise, you simply would have to look up in those tables, which are memory themselves, every time you need to figure out where in memory you should be looking in the first place, which is horrible. Okay? So that's called the TLB cache, the translation look ahead buffer. Right? So there is a TLB cache. Okay? Now, this cache is very important when it comes to switching between processes, because this cache is quite large. And in fact, the cache head needs to be wiped out when you switch processes. Why? Different processes are going to have different virtual memory systems. If you don't wipe out the cache, you're simply going to use the mapping that the other process used, and you're going to go in the wrong place. Okay? Truly, truly bad. I mean, first of all, the process doesn't run what you think it runs. Plus, this is a security hole, because a process can access the memory of another process. Now, wiping out the TLB, it's a very fast operation. You can just tell the hardware, wipe it out. What's slow is to fill the TLB again, because now you're going to miss everything in the TLB, and you have to work in the hard way to go and switch and do. And now, we have an idea of why we say lightweight and heavyweight for threads. If you share the same virtual memory system table, you don't need to wipe out the TLB. Now, the registers you still need to save, but no wiping of the TLB, right? So that essentially means that if the operating system keeps the same core, running the same process, but different threads in the process, it doesn't have to pay this super heavy price. So this is really the big saving. This is where the lightweight versus heavyweight really comes into play, because you still have to save registers. Why? 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 So what I want you to understand is that some people decided at some point to do it this way, and it's very important to ask why. This is what I tell my 11-year-old, and I started to tell my 6-year-old. Ask why.
Because maybe two threads of the same process are working at the same time.
So?
They may override their, if they share the same register, they may override their mode.
So?
We will have a code or a process for managing concurrency
Well, but OK. Yes. So let's see other ideas.
If they had the same virtual memory space and the same registers and like the same instruction pointer, they would be executing exactly the same thing. I think you don't want that.
Right. So let's make first a distinction, OK? So the first distinction I want to make is same registers, right? Well, these registers are this physical thing, right? I mean, they're just some very special cache-like thing, let's say, OK? They just have nice names, and you can refer to them in the instructions, OK? So that's nice. Every core definitely is going to have a different set of registers. And in a funky way, actually, even every core could have multiple sets of such registers to do other kinds of trickery. Okay. By the way, modern hardwares are all about tricks. I mean, lots of tricks. Okay. So what exactly is going on in there is even more complicated than what I'm describing, which is already complicated. So those are the physical things. Now, running mean, what exactly does running mean? Actually, that's the first question to ask. What does it mean that some program is running? That essentially means that the processor is following a certain set of instructions that we associate with whatever the executable is. So what precisely that means is, well, the program is encoded at the lowest level in some sort of bits. They are somewhere in memory, and those instructions, the low-level instructions, specify once you execute this instruction what to do next. So implicitly or explicitly. So the instruction might say, do this manipulation with the values of registers, but it might also say, jump at this location in memory. That can be relative or absolute. For example, go back 15 bytes. That's one of, those are called jump instructions, right? Especially conditional jump instructions that are everywhere. If this is true, go back 15 bytes and start executing there. So there is a very special register, and this is how the magic happens, actually. There is a very special register that tells you where you are now in the execution of the program, okay? So it's called the IP instruction pointer. So the instruction pointer is a special register that tells the processor, this is the location in memory that describes your next instruction. So when the processor runs, it looks at the location in virtual memory where the IP points out, interprets that instruction, and then acts accordingly. But implicitly, act accordingly means move to the next instruction if it's not a jump instruction. So there is an implicit increment of the IP, which is complicated itself because some instructions span 3 bytes, some instructions 5 bytes, right? So the instruction you execute now specifies at least how to increment the IP counter, right? So technically, in order to switch execution from one program to another, you just have to switch the IP register, okay? And funny enough, programs can change their own register, right? So essentially, a function call, right, especially a more like a closure thing and not necessarily a function, right? Or forget about that, exceptions, continuations can be implemented by just manipulating the IP pointer and nothing else. So you simply can jump anywhere you want by putting a value into the IP register, and there is a special instruction to do so. Now, that's the minimum requirement in order to execute something, to change the IP register. Now, of course, the trouble is, if you change the IP register and you're not saving some of the state, it's hard to come back unless you know what you're doing, right? Sometimes you do know what you're doing and you say, hey, it doesn't matter because I'm jumping to a place that anyway is going to assume that the registers are dirty. So it's going to start putting values into them and not assume that correctly it had some value before. But if the operating system is interrupting a process or whatever else it's interrupting, the operating system doesn't know, doesn't have any extra semantic about what it's okay and what's not okay to do with the process. So it has to assume the worst, which means it has to assume that all the registers are used, which means it has to save the registers. But that's just convenience at the level of the operating system because we didn't bother to tell the operating system at any point in execution which is the set of registers that it's okay not to recover, right? If your program just uses 2 registers, operating system, I mean, that's a nice optimization, could just save those 2 when it preempts this process and then just recreate the value of those 2 because you're only using the 2. It doesn't matter that you have another 300, right? So what I want you to understand is you could have these other implementations in which you don't save everything, in which you save only what you used, right? And that would be an optimization. So when an operating system is doing this switch between processes, it doesn't have to save the registers if it would magically know which ones are not needed, right? So in particular, if it knows you don't use AVX instructions, it might not save the AVX registers, and that's a tremendous saving. This thing with the saving can actually be used when you do function calls, right? By the way, what's a function call? At the low-level hardware, forget about high-level languages in which you say, oh yeah, you write call the function, and then the function gets called. What do functions call do? So it's essentially a jump with a way to come back. Which function calls have that return. How would the return be implemented?
Return to the same mode.
Yes. So the return is some sort of a figure out what the old value for IP was and jump there, right? So it's a job, it resets the value of the IP. Now, it turns out that you do want to have some convenience even at the level of the hardware. So these things are implemented as higher level mechanisms. Very low in the processor is really just a jump, right? So suddenly, there is something else that's interesting and comes into play. And it was introduced specifically to deal with functions because they are essentially everywhere in all the programming languages, which is an automatic way to save the state of a function. For example, functions have local variables, right? And you need to save the value of the local variable because when you return from another function call, you still want to see the view that you had before the function, okay? And that's where the stack comes into play, right? So we have stack. So the stack is essentially just a region of memory where you have extra storage where you can put things, but has this magical property that it's very easy to recover the state of a previous, to go back in the state because it's just a jump in the stack, right? So you don't only have an instruction pointer, you also have a stack pointer, right? So the stack pointer is another special register, and by essentially putting another value in the stack pointer, usually increment or decrement it. Incrementing it is, decrementing it because stacks go backwards. Why do stacks go backwards, by the way? No, but it's a matter of implementation. I mean, why not make them go forward? No, I mean, forget about the data structure itself. Even if you do that, the normal implementation, if I ask you to implement a stack in C, you're going to implement it in a natural way in which it starts here and it grows with increasing values of the address space. In all modern processors, it goes backwards. Why?
Size of the stack is unknown.
So?
We have to specify a size of the stack, therefore it decreases. This 128, we can only store 128 spaces.
Right. So it's basically a trick they came up with early on in processors to make the life easier, and they just kept the trick. It's not really needed in modern processors. And actually it turns out that you can't even do what they were doing before because of the multi-threading. So the trick with going with the stack backwards is good for non-multi-threading systems, but is not particularly good for multi-threading systems. So the trick is related to the fact that you have no virtual memory, so you're at the, let me draw it here, right? So this backwards going stack was introduced before virtual memory was introduced. So they had no way to manipulate the memory layout through the virtual memory system, so they were stuck with some sort of a very flat view. And then they said, hey, this is the address 0 and this is the FFF, whatever it is here. We start laying out, so this is how DOS was working. The operating system at the very bottom, then the program that runs higher up, then the data, this is the program. This is the data for the program. Then the heap is going to grow in this way. And let's make the stack go in the other way so that we don't have to think about we are going to use a lot of stack or a lot of heap. When they meet, it's a disaster and we kill the program or whatever. Right? So essentially, for convenience, you make one go forward and one backward, not to worry about where to cut the line. Right? And then, hopefully, the heap never meets the stack, and that's it. What's the heap? It's this, some sort of dynamic allocation. Right? Now, why am I saying that this is not possible in systems that have multiple threads? Because the stack is something that the threads can't share. Why? Because the stack now is part of the state. Sharing the stack means sharing the history of executing functions, which in normal multi-threading programming is a big no-no. You can't. I mean, every thread has its own life and its own history, and the history is part of who the thread is and what the thread does. It's not only the registers now. It's the stack, right? Because when you do a return from a function from one thread, you don't want to jump to a place where another thread wanted to jump before. Okay? Unless you have programming languages that want to do that. That's a different story. Okay? So then suddenly you can't have all of those stacks start from the end, right? Because there is only one end. I mean, even virtual memory or non-virtual memory. And we already said that we don't want to give a different virtual memory space for every thread. It's crucial that we don't. No TLB misses. Big, big, big performance hog. Right? Good. That means multiple stacks and deal with stacks. So now we have a little bit of a problem there, and we understand a little bit the distinction between processes and threads. So processes, complete isolation at the level of the operating system, different virtual memory system unless they do some special system calls to do some shared memory. A slightly different story. Threads are different execution points. That precisely means that they have their own set of registers, so they remember the state register-wise, and they have their own stack, so they remember their entire history. They do share everything else, in particular the heap. This is where big problems come when it comes to multi-threading processing. The fact that the heap is shared, and because it's shared, if one thread changes it and the other thread is reading it at the same time, you could have this weird behavior in which bad stuff happens. Yes?
If contains also global variables, right?
Yeah, but what's global variables? So global variables are an abstraction in programming languages. We're talking about processes. Where are the global variables? Data. So this, in fact, is the organization in the layout of the programs, except that you don't need this part, because the operating system, it can manipulate the virtual memory system. So it simply starts mapping the program at 0 because it doesn't show you a lot of the memory that's actually using in the real memory. So this is the virtual memory organization most operating systems have. You start at 0, you start laying out the program, you start laying out the data, and that's whatever you call global variables, and then you start the heap. And the stacks are all up here somewhere. Yes?
But data, data is not shared. Each thread has its own data.
What does data mean?
Local variables. I think
But what are local variables? Okay, registers is one of them, but stack. I mean, a lot of local variables live on the stack. So what I want you to understand is, again, big words flying all over the place. There are no local variables at the lowest level. There is only the stack and the registers, right? So who decides what goes in the stack and what goes in the registers? Yes. That's why we use compilers and we don't do this stuff by hand, not to go insane with all of these complications, right? So a good compiler is going to have the tendency to put a lot of things into registers as opposed to put them on the stack.
but I think global variables are in here because it's shared amongst all threads.
Want to bet? Okay, no, they are here. Trust me. So look, everything, if this is virtual memory, everything here is visible to all the threads. There is no distinct. Actually, the hardware doesn't even care where the data is and where the heap is. It's all bits. It does care about this region, though, because you'd usually want to allow execution only for bits that are in this region, because otherwise you can get all kinds of viruses and security exploits and whatnot, right? So this data, usually all of it, it's marked as read-write but no execute in order to prevent funny stuff going on. But the processor couldn't care less which is data and which is heap, really. The heap is just some virtual organization on top of those bits, right? And the operating system provides some help. But in fact, you need no heap. Any idea how I can access other things that are not part of the normal heap? Could I get some memory that's neither data, nor heap, nor stack in a modern operating system? Yes, mmap, right? So there are other mechanisms that allow you to map virtual memory to physical memory that has nothing to do with heap and is not heap. And by the way, that's how you can do some of the cleverest tricks. The heap, because it's a shared resource, is not particularly good, right? You could do other things. I'm going to describe some of them because it looks like we need to build up this knowledge, right? You can do other things to make memory be correctly mapped. And then it breaks these boundaries of what's heap and what's not heap and what's stack and what's not stack, right? So this is my encouragement for you. Zoom in on what these things mean. Because this now becomes very important. Because I have to save the stack, because every thread needs a stack, that means there is already an upper bound on how many threads I can have in a system. Each stack is at least 4 kilo. You take the amount of available memory and divide it by 4 kilo, and that's how many threads you can have, and that's it. Right? So a strict limitation in how many threads you can have is how many stacks you can afford, even ignoring all the register stuff, right? So that essentially means that there is a practical limit of about 10,000 threads usually because of problems with already committing memory for the stack. You're going to waste a lot of memory for the stack otherwise, okay? That means that if you want to implement 1 million actors, you'd better not have a thread per actor. And we're going to come back to this later. But then you have to give up something. So what do you give up with actors? The stack, right? That means whatever you keep inside an actor has to live on heap. And you're not going to have those local variables flying around. Essentially, you give up your local state. You only have some sort of a state that others could get to, but the language maybe prevents them to do so. This is what languages that have protection offer, like Scala. Okay? So one of the key ingredients to have a good implementation for actors is not to map them to threads. If you don't map them to threads, in principle, you could have a single thread in the system that runs all the actors. Why you would not do this? Well, first of all, you need one thread per real core, because otherwise you're not using all the cores. The operating system has no way to map a single thread of execution on 5 execution units, right? But I'm going to mention another reason next time that's related to blocking I/O, right? So all of these details matter because, by the way, even in Scala, you can say, hey, please add more real threads because I'm running out of something, and we're going to talk about that later. Okay, so I'm going to fix the attachment problem so you can read the assignment and start working on it, and start right away. I mean, you have to get code running, okay, to submit running code.